Transformers have taken the AI world by storm. Their ability to process information in parallel has revolutionized natural language processing. This has led to breakthroughs in translation, text generation, and more. However, the quest for artificial general intelligence, or AGI, requires a diverse set of tools. We must explore alternative architectures. These offer unique strengths and address specific challenges. The field of AI is teeming with innovative architectures, each with its own strengths and weaknesses. Understanding these nuances is crucial. It allows us to develop AI systems tailored for specific tasks. This exploration beyond transformers is not about replacing them. It's about enriching the AI ecosystem. We need diverse approaches to solve the world's increasingly complex problems. This video delves into some of these unsung heroes of AI. We'll explore their inner workings and showcase their relevance. We will see how they excel in specific domains. Examples will be used throughout to demystify these concepts. Join Vlab Solutions on this journey beyond the realm of transformers. Discover the exciting possibilities that lie ahead. Recurrent neural networks, or RNNs, are the time travelers of the AI world. They excel at processing sequential data. This includes tasks like speech recognition, natural language processing, and time series analysis. RNNs possess a unique ability. They maintain a hidden state. This state acts as a memory, allowing them to remember past information and use it to influence future predictions. Imagine predicting the next word in a sentence. An RNN processes each word sequentially, updating its hidden state with each word it encounters. This hidden state captures the context and meaning of the preceding words, enabling the RNN to make accurate predictions about the next word. However, RNNs have limitations. They struggle to remember information over long sequences, a problem known as the vanishing gradient problem. Fortunately, advancements like long short-term memory, or LSTM, networks address this issue. LSTMs introduce sophisticated gating mechanisms that regulate the flow of information through the network, allowing them to effectively capture long-range dependencies in data. RNNs, with their inherent understanding of sequence, remain highly relevant. They power virtual assistants, enable real-time language translation, and are essential for any task involving sequential data. As we generate and consume more data, RNNs will continue to play a crucial role in shaping our future. Convolutional neural networks, or CNNs, are renowned for their prowess in image recognition. They excel at identifying patterns and objects within images, but their capabilities extend far beyond this domain. CNNs are now being applied to diverse fields, including natural language processing, drug discovery, and even financial forecasting. The key to CNN's versatility lies in their unique architecture. They employ convolutional filters that slide across the input data, extracting local features. These features are then combined hierarchically to form higher-level representations. This hierarchical feature extraction enables CNNs to identify complex patterns and make accurate predictions. For instance, in natural language processing, CNNs can be used to analyze text sentiment. They treat sentences as one-dimensional images, where convolutional filters extract features from groups of adjacent words, capturing local semantic relationships. These relationships contribute to the overall sentiment of the text. The ability of CNNs to learn hierarchical representations from grid-like data makes them incredibly versatile. Their applications continue to expand. They are no longer limited to the visual realm. Their ability to analyze patterns in complex data makes them an indispensable tool. They are essential for a wide range of applications across various domains. Attention mechanisms revolutionized natural language processing. They allowed models to focus on specific parts of the input, leading to significant improvements in tasks like machine translation and text summarization. However, these attention mechanisms can be computationally expensive, limiting their scalability to longer sequences or larger datasets. Sparse attention mechanisms offer a solution. They selectively attend to only the most relevant parts of the input, reducing computational complexity without sacrificing performance. This is achieved through various techniques, including local attention, where the model only attends to a fixed window around each word, and hard attention, where only a predetermined number of input elements are considered. Imagine summarizing a long document. A sparse attention model would identify and focus on the most salient sentences, conveying the key information while ignoring less informative sentences. This targeted approach allows for efficient processing, ensuring that the model captures the essence of the document without being bogged down by extraneous details. Sparse attention mechanisms represent a significant step towards more efficient AI models. They enable us to handle larger and more complex datasets, opening up new possibilities for applications in fields like healthcare, finance, and scientific research. As we strive for AI systems that are both powerful and efficient, sparse attention will undoubtedly play a crucial role. In many real-world scenarios, the order of elements within the input data is irrelevant to the underlying task. Consider predicting the properties of a molecule. The arrangement of atoms within the molecule doesn't change its chemical properties. Traditional neural networks struggle with this concept. They are sensitive to the order in which data is presented. Permutation equivariant architectures address this challenge. They are designed to be invariant or equivariant to permutations of the input elements. This means that shuffling the input data doesn't affect the model's output or leads to predictable changes. This property is crucial for tasks where the order of elements is arbitrary. These include protein structure prediction, drug discovery, and particle physics. Imagine a model predicting the energy of a molecule. A permutation equivariant model would output the same energy value. This is true regardless of how the atoms are ordered in the input representation. This property is crucial for accurately modeling physical and chemical systems. In these systems, the order of elements is often arbitrary. By incorporating permutation equivariance into AI architectures, we can create models that are more robust, efficient, and capable of handling complex real-world data. This opens up new avenues for scientific discovery. It leads to the development of innovative solutions in various fields. Meta-learning takes the concept of learning to a whole new level. It focuses on building AI systems that can learn how to learn. Instead of being trained for a specific task, meta-learning algorithms are trained on a variety of tasks. This allows them to acquire the ability to adapt to new, unseen tasks quickly and efficiently. Imagine a meta-learning algorithm trained on a dataset of different image classification tasks. It learns to identify the underlying structure of these tasks. When presented with a new image classification task, it can leverage its prior experience. It can quickly adapt to the new task with minimal training data. This ability to learn how to learn has profound implications for the future of AI. It paves the way for more adaptable and versatile AI systems. These systems can quickly adjust to new situations and solve problems they haven't encountered before. This is crucial for developing AI that can operate in complex, dynamic environments. Meta-learning is still an active area of research. It holds immense potential for the future of AI. As we strive to create more intelligent and autonomous systems, meta-learning will play a pivotal role in enabling machines to become true self-learners. Inspired by the dynamic nature of biological neural networks, liquid neural networks introduce a new paradigm in AI. Unlike traditional neural networks, where the structure is fixed during training, liquid neural networks can adapt their structure and connections over time. This allows them to continuously learn and evolve in response to new information. These networks utilize a set of differential equations. These equations govern the evolution of neuron activations and connection weights. This dynamic structure enables liquid neural networks to handle continuous streams of data. They can adapt to changing patterns and relationships within the data. Imagine a liquid neural network used for real-time traffic prediction. As new traffic data flows in, the network can adjust its internal structure. It can capture new traffic patterns, road closures, or accidents. This allows it to provide accurate and up-to-date traffic information. The adaptability and continuous learning capabilities of liquid neural networks make them well-suited for complex, dynamic environments. They offer a glimpse into the future of AI. In this future, AI systems will be more organic, adaptable, and capable of lifelong learning. While transformers have undoubtedly revolutionized the field of AI, it's essential to recognize that they are not a one-size-fits-all solution. The quest for artificial general intelligence demands a diverse ecosystem of architectures. Each architecture offers unique strengths and addresses specific challenges. RNNs, with their ability to process sequential data, remain crucial for tasks involving time series analysis and natural language processing. CNNs, known for their image recognition prowess, have expanded their reach far beyond the visual realm. They are now applied to drug discovery, financial forecasting, and various other domains. Sparse attention mechanisms address the efficiency concerns of traditional attention models. They pave the way for handling larger datasets and more complex tasks. Permutation equivariant architectures excel in scenarios where the order of elements is irrelevant. They open up new possibilities in fields like drug discovery and material science. Meta-learning pushes the boundaries of AI by enabling systems to learn how to learn. This fosters adaptability and versatility, crucial for navigating complex and dynamic environments. Liquid neural networks draw inspiration from biological systems. They introduce a paradigm of continuous learning and adaptation. As we venture further into the age of AI, it's imperative to embrace this diversity of architectures. This will allow us to develop tailored solutions for specific challenges. By fostering a rich and varied AI ecosystem, we can unlock the true potential of artificial intelligence and create a future where humans and machines collaborate to solve the world's most pressing problems. Thanks for watching.